This is a lesson on hydrolysis. So hydrolysis involves the decomposition of water. And if we look at this, we can see that it is a redox reaction. In water, hydrogen has an oxidation state of +1, and oxygen has an oxidation state of -2. Hydrogen gas, elemental, has an oxidation state of 0, and the oxygen has an oxidation state of 0. So the water gets both oxidized and reduced. The hydrogen gets reduced, and the oxygen gets oxidized. So to do that, we're going to set up an electrolytic cell. So we have a PS, a power supply, and these are representing two test tubes filled with water that are upside down in the water. So there's all water all over. And then we have two platinum electrodes, one in each of our inverted test tubes filled with water connected to the power supply. So when we turn on the power supply, we're going to get both oxidation and reduction. So if we look at our reduction potential chart, we can see here that we have two water molecules going to oxygen gas, hydrogen ions, 4 electrons, and so our E0, since it's an oxidation, when we reverse it, will be a negative 1.30. So we have 2H2O going to O2 plus 4H plus 4 electrons, and that E0 is a negative 1.23 volts. Then, so this is our oxidation. That's our oxidation half reaction. For our reduction, we check our chart again, and so that's all the way down here. Now we have water taking 2 electrons and turning into hydrogen gas and hydroxide ions with an E0 of negative 0.83. So that is, so we have 2H2O plus 2 electrons going to H2 gas plus 2OH minus, and our E0 equals negative 0.83 volts. So at one of our electrodes, we'll have the oxidation. So we'll just put that over here. So oxidation and O2. So O2 is produced. And then in our other test tube, we'll get the hydrogen gas, and we'll have our reduction where hydrogen gas is produced. So for our reduction, H2 produced. And our E0 for the cell would be a negative 2.06 volts. So this does not happen spontaneously. That is why we need a power supply to overcome the negative E0 and make this reaction happen. So to add up these to get our total overall reaction, we have 4 electrons here, we need 2 electrons here, so we have to multiply everything by 2. And so then we end up, we have 2 waters plus 4, so we end up with 6 H2O. And then the electrons 2 and 2, 4 and 4 will cancel, yields O2 plus 2H2 plus 4H plus 4OH minus. So now, the H plus and the OH minus, that's going to react to form H2O. So we're going to get 4H2O. The K for that is really large. So we have 4 water here, 2 water there, so we're going to subtract 4 waters from each side. And that ends up with 2. So we end up with our original decomposition equation. 2H2O yields O2 plus 2H2. So that's gas, gas, and that is liquid. All right, so we want to remember that oxygen gas is produced at the anode, and the hydrogen gas is produced at the cathode because the hydrogen gets reduced. Oh, and I almost forgot something really important. For this to happen, we can't just have plain water. We've got to have an electrolyte in here. So we could have some hydrochloric acid, we could have some sulfuric acid in there, or we could have a salt. We have to have some electrolyte, some ionic compound that's going to give us ions in the solution for that reaction to occur. Okay, so how many moles of hydrogen gas would be produced from running a 10 amp current for 3 minutes? And we're, of course, referring to the cell that we just talked about. All right, so dimensional analysis, amp, again, we write that as 10.0 coulombs for every 1 second. X moles of H2 equal 3.00 minutes. Convert the minutes to seconds. 60 seconds for every 1 minute. Now we have seconds. Now we use our amp conversion factor. So 10.0 coulombs for every 1 second. Seconds cancels, minute cancels. As soon as we get that coulombs, we use our Faraday's constant conversion factor. So we have 96,500 coulombs for every 1 mole of electrons. And then we go back to our half reaction to figure out how many moles of electrons. So H2 takes 2 moles of electrons. You could say 2H2 takes 4 moles of electrons. It's the same thing. So for every 1 mole of hydrogen gas produced, there needs to be 2 moles of electrons. So 1 mole of H2 for every 2 moles of electrons. And that gives us the unit that we're looking for, moles of hydrogen. And let's see, do I have that answer? Yeah, I have 0.00933 moles of hydrogen gas produced. Okay, so now we're going to look at the electrolysis. So that is breaking something down with an electric current, forcing a current through a wire, of potassium bromide. And we're going to look at solid potassium bromide, molten or liquid potassium bromide, and dissolved or aqueous potassium bromide. So let's start out with solid potassium bromide. So it looks just like table salt, white ionic compound. We have a structure, a crystal lattice of alternating ions. So if we put some electrodes in there, attach this to a battery, to a power supply, nothing happens. No electric current can pass through the solid KBr. And that is because the valence electrons in the potassium ions and the bromide ions are localized. Our valence electrons are localized. So this means they are not mobile. They cannot travel from atom to atom to atom like they do in a metal. Our valence electrons stay with the nucleus. They stay with the atom. So no electric current through the solid KBr. Does not conduct electricity. All right, how about molten KBr? So now we're going to melt the KBr, and our melting point is 734 degrees C. So ionic compounds typically have high melting points because the ionic forces between the compounds, the coulombic forces of attraction, are so strong that it takes a lot of energy to break those forces and enable those ions to be able to move past one another. All right, so to break apart our KBr, of course, we need a power supply and 2 electrodes here. So how are we going, or what is going to happen? When we have KBr, we have potassium ions and bromine ions. So in terms of what is going to happen with the power supply, the K plus is going to gain an electron to become neutral potassium. There's no way that K plus is going to be K2 plus. I mean, that's crazy just even saying it. And then the bromide ion can lose its 1 electron and go back to being neutral bromine. So our K plus is going to take the electron and become potassium. So this is our reduction. And then for the bromine, so we have Br minus, that is going to go to neutral bromine. So of course, Hofbrinkel, Br2, so we're going to need 2 bromines. And, oh, this gets oxidized, so plus 2 electrons. So let's look at our E zeros here. There's our chart. So for the potassium, so that's right here. So the reduction of the potassium ion is a negative 2.92. And then the oxidation of the bromide ion to neutral bromine, that is right here. We flip it because it's oxidation, so we get a negative 1.07 volts. So the E0 for the cell then is 3.99, negative 3.99 volts. And this is the way that we can get neutral potassium metal. So if here, this is where the bromine ions can come up to the plate and they're going to give their electrons. So our electron flow will go that way. And then here we will have the potassium ions that plate onto our electrode. All right, and then the next is we're going to look at when we have potassium bromide dissolved in water. So here we have K plus aqueous and Br minus aqueous. And we have water molecules. And we saw at the beginning of this lesson that water can be oxidized and water can be reduced. So when we run our power supply, nature is going to take the path of least resistance. It's going to oxidize and reduce whatever is easier. So we're going to consider the candidates. So our oxidation candidates are, well, which can this be oxidized? No, potassium is not going to lose electrons and go to K2 plus. That's crazy. So the bromine can be oxidized. The bromide can be oxidized to bromine. So Br minus is a candidate, and then water is a candidate. So what we're going to do is look at the E0 for both of these and pick the one that is greater or less negative. So from our chart, we already found that the bromine for oxidation was negative 1.07 volts. And water for oxidation is negative 1.23 volts. So the bromine has the least negative, it has the greater value. So the bromide is what is going to be oxidized. So we're going to see Br minus going to Br2 plus 2 electrons. And then, of course, we need 2 of those. So now we have to look at our reduction candidates. So what can be reduced? Well, potassium, K plus, could be reduced to potassium metal, and the water can be reduced. So look at those values. So the potassium, the E0 for the reduction is negative 2.92 volts. And for water, it is negative 0.83 volts. So the potassium is not going to be reduced. We are not going to get any potassium metal. The water is what is going to be reduced. And so then we have our reduction half reaction, 2H2O plus 2 electrons gives us H2 gas. Remember, hydrogen is produced at the cathode, plus 2OH minus. And so our E0 of our cell is the E0 of the oxidation, negative 1.07 volts, plus the E0 of the reduction, negative 0.83 volts. So we get negative 1.90 volts. So of course this is non-spontaneous. That's why we need a power supply to overcome that voltage. So whenever you have an ionic compound in water and you run electrolysis, you have to check if water is going to be either oxidized or reduced. So we're looking for the most favorable E0, the least negative E0. And that's it.